Okay, that was all a lot of talk. Let me show you how powerful this trajectory optimization and trajectory stabilization or feedback is by telling you a little bit about an example that we've done here in the lab over the last couple of years. Okay, so we were really interested in, I am and continue to be interested in birds and how beautifully they fly. And we looked and tried to ask the question, can we make an airplane that can do something a bird can do, like land on a perch? And I mentioned this in the introduction lecture, but let me tell you some of the details now. Okay, so the problem is take a fixed wing airplane with only a controller at the tail and see if we can make it land on a perch like a bird. All right, so just to tell you why this is hard, if you take an airplane wing and put it make it fly forward in air, when the wing is at a low angle of attack relative to the oncoming flow, the air bends around the wing, and actually piecewise linear models of the fluid dynamics here, of the lift and drag forces, they work very well. Okay, if I were to change the angle of attack of my wing relative to the oncoming flow, if I were to pitch my nose up as I fly, then the air just bends around the wing, and in fact, still linear approximations of how the lift and drag change as a function of my angle of attack or my control inputs, they work very well. Okay, but something dramatic happens when I go up and I past a critical angle of attack where I stall my wings, right? Now the air really physically can't quite bend around the wing, cannot stay attached, it doesn't make that turn. What happens is it pulls off, you get an unsteady flow behind here, you get a vortex that develops and eventually will shed, and you end up with a time varying dynamics in here, which is very nonlinear. It changes in a nonlinear way as a function of angle of attack. And this has generally been considered much, much harder to model, come up with simple models to describe, and much harder to do control. So most aircraft control systems today avoid this regime completely. Okay, so even our best fighter jets will have an angle of attack limiters, which just the autopilot will prevent the pilot from going into a post-stall flight because it's a dramatic change and hard to control. So it's kind of fun to think, birds do go into post-stall all the time, and airplanes don't. Do birds achieve a dynamic advantage for doing it? So we did a quick dimensionless analysis of perching, right? So we tried to compare two things that are very different size, right? We have a bird with mass m, some wing area. All these numbers are much smaller than a number for a plane. The only way to compare them fairly is to scale out the effect of those dimensions, okay? So we're going to think of scaling over distance as well too. It requires some distance x to slow from velocity v0 to vf. So the dimensionless number, that's sort of a more fair comparison of very different scale systems, is the dimensionless drag coefficient. Okay, so this is a dimensionless measure of how much braking force you're achieving. We decided to average over distance as opposed to average over time, because that actually gives the advantage to the planes. If we have it's harder for us to get a good score averaging over distance. Okay, and the distance average drag coefficient, if you care, turns out to be something like this. All right, so but here, let me give you a couple reference points. Okay, so a Boeing 747, standard Boeing, if you're doing a runway landing, let's say at Logan Airport here in Boston, then that airplane will get an average drag coefficient of about a 0.16. Okay. Now there's been a lot of great work on super short and extremely short runway landings by fighter jets. This one uses thrust vectoring, so it sits on its tail to maintain some control authority even though it's at a very high angle of attack. This one's coming in at about a 24-degree angle of attack, the X-31, and it gets an average drag coefficient of about 0.3. So it is slowing down much more significantly due to drag forces than a 747, and accomplishing this much shorter runway landing as a consequence. But we wanted to know how well birds are able to stop. Okay, so I would love to have numbers from the most aggressive hunting birds, the predators of the forest and everything like this. But my good friend at Harvard, Andy Buener, and his lab, they study pigeons. So I have data from pigeons. And in fact, Andy has done a great job of convincing me that the pigeons are not just the ones they happen to study, but they're actually one of the most adept flyers in these sort of urban environments. They've been trained, and they're actually very agile flyers. Okay, so what do you think? What do you think the common pigeon scores in the average drag coefficient. Turns out the common pigeon gets a 10. Okay, so he's flapping his wings, he's doing lots of things to get a number that's big. But let me just tell you, this is a ridiculous number, right? Because, well, let's put it in perspective. If you wanted your 747 to achieve an average drag coefficient of 10, that would mean it has to be able to go from its 450 mile an hour cruise speed to approximately 0 in about 40 meters. That's how fast these birds are stopping. I mean, aerodynamically, it's impressive, right? But what's really impressive is that this bird, through flapping and through high angle of attack aerodynamics, is exposing itself to this ridiculous sort of parachute-like braking force. It's slowing down incredibly quickly. And during this incredibly complicated parachute deployed sort of landing, it's able to achieve an accuracy to put its foot on a wire when our airplanes are only able to sort of hit a runway. Okay, so it's somehow the most impressive part is not just that it exposes itself to such dramatic forces, but that during those dramatic, complex forces, it's able to achieve exquisite precision. So we want to see if we can do some of that with the planes. Maybe all this control ideas could help us make an airplane do the same thing. So here's the experiment. We've got a flat plate glider. There's no propeller. Turns out if you want to stop, you don't actually need a propeller, and propellers add extra complexity to the fluid dynamics, so we kept it out to make sure we understood everything. There's an exercise in building the simplest possible plane to help us study the experiment. So continuing that theme, we kept the computers off board. We put onboard motion capture markers and put it in a motion capture studio so we could track the plane in real time without having any onboard computation. The only thing on board was a receiver and a hobby servo. There's exactly one actuator, which is the elevator here in the tail. Okay, we shot the plane a bunch of times in this motion capture environment and did system identification to try to build models of the post-stall airflow. So this is a plot of the lift and drag coefficients backed out from double differentiating the motion capture data twice, okay, as a function of angle of attack. And it turns out textbook flat plate theory, which includes the post-stall regime, does a very nice job of explaining the lift coefficient. It does a reasonable job of explaining the drag coefficient, especially if you were to look inside this data here, which looks like messy, noisy kind of data. There's actually a pattern here. There's a periodic solution happening here as the vortices are shed, and we're actually able to see from our motion capture data the vortices pulling off the plane. We see as the airplane gets tugged around. So this is actually the flat plate theory does not capture the time-varying aerodynamics, but it does a pretty good job of averaging through them. Okay, the moment coefficient is by far the worst, but still, the flat plate theory gives us a pretty good model to start from, and then we do a little bit of system identification work on top of that to capture the differences between the flat plate theory and the the statistical data. That gives us this this pretty simple model. Okay, so we have a XY position of the plane here. We've got aerodynamic forces coming from the wing. For a flat plate, it's at the mean aerodynamic chord, even though most other airfoils would operate from the quarter chord. This one's from the mean aerodynamic chord. We have an aerodynamic force. Same thing, we're going to model the elevator as a second flat plate. Okay, we've got a pitch we care about, x, z. We have an angle of the elevator. That's our state space. Okay. And our control, we're going to assume it's a 7-dimensional state space. There's an odd number because we're going to assume that the inertia of the tail is negligible in the dynamics of the airplane, and we're going to have direct control over the velocity because that's what we had from our hobby servos. Okay, it turns out if we take our model, put it into Drake, and do some basic trajectory optimization, this is a direct collocation method now. We have an initial position here, z at 0. We're going to start 3.5 meters away from the perch. We're going to try to find a solution which gets us to the perch using trajectory optimization, and it works just great. So that's how fast it works, and that's slowed down for animation purposes. But trajectory optimization, showing the intermediate runs of the trajectory, finds a solution and gets us to the perch. It works extremely well. Okay, and it turns out it works on the real plane as well. So if you play that trajectory out on the real plane by itself, it doesn't work at all. it doesn't work very well, but with feedback we can make it land on the perch almost every time. This is high speed, slowed down about 11 times. The entire trajectory takes about 0.8 seconds. And just to show you some data here, we actually built a wind tunnel just to take pictures to make sure we understood the post-stall aerodynamics. We put smoke on the leading edge of the wing and launched the plane. And in fact, we could see that the vortices were pulling off at exactly the same rate we predicted from looking at the time-varying elements of the drag data. And here's Joe demonstrating just how robust the system is. Now this is not just LQR, it's LQR plus a different idea. We're going to call it LQR trees. We'll talk about it soon. But to give you a sense that with some good feedback design, you can make this airplane really land on the perch pretty much every time. Which is impressive since it has only a single actuator on the tail to control the 7 state variables. Okay, now without feedback, if we just played the open loop trajectory every time, we would hit the perch sometimes. But if I change the initial speed, this is a plot which shows different initial velocities and different distances from the perch. This is the closest distance the plane went to the perch over its entire trajectory. So sort of a generous score of how well it did. Then it hit the perch from most of the time within some tolerance from the initial conditions on which we planned, but this was hard to achieve in general, and we missed the perch if we're off with a slightly different initial condition. Now, obviously the initial conditions are high dimensional. This is just plotting one dimension of it. But with the feedback control, we can hit the perch every time. And now the picture you should have in your head, really, is that we have this nominal trajectory we get from trajectory optimization. Bunk, goes to the perch, right? On top of that, we design a feedback controller. And what the feedback controller is giving us is it's a linear feedback controller. It's based on the linearization of the dynamics along the trajectory. But what it gives me is the ability to recover from some volume of initial conditions that are off the trajectory, where the linear system is a good approximation of the nonlinear dynamics. And in this sort of tube, we can expect the linear controller to work well for the nonlinear system. And in fact, to tolerance, given some final specification of what an acceptable error is what the landing mechanism can accommodate, we can back out what's the set of initial conditions where the linear controller works for the nonlinear system. And guess what? We're going to do it with Lyapunov methods like we talked last time. But we'll have to extend those to the time-varying case as well. Okay, so this works very, very well. It's a good recipe, and really this is the system that made me believe in the trajectory optimization plus feedback along trajectories, linear feedback along trajectories approach. I thought that there was no way that a linear controller along the trajectory would do very well at all on this complicated, highly underactuated system. But in fact, if you watch the system, even with just a simple time-varying LQR controller on it, you'll see, to my eyes, having watched a lot of these planes fly a little bit, you'll see very different trajectories where the plane starts with too little energy, and so it actually dips down to gain energy and speed up and get to the perch. You'll see different trajectories that start with too much energy and it goes post-stall earlier, takes a high trajectory and gets back to the perch. You'll see a pretty large repertoire of responses that all come out of the linear controller on the nonlinear trajectory, on the optimized trajectory. And this was the moment for me where I started believing in the power of linear control and its utility in designing nonlinear systems. Okay, hope you enjoyed.